Hello, my name is Kejun Huang. We're sorry that none of us can come to the conference and present the paper for you, and we thank Yanis for playing this video for the presentation. So this paper is about learning hidden Markov models from pairwise co-occurrences with application to topic modeling. So hidden Markov model is a very well-known model in machine learning. Basically, we look at two sets of random processes. The xt's are categorical variables taking capital K number of possibilities, and they form a Markov chain characterized by this transition probability. And for each of the latent variable xt, we have an indirect observation denoted by yt, which is again categorical, taking capital N number of possibilities, and is characterized by emission probability of yt given xt. With this graphical model, it's easy to write out the joint probability, which factors into this form, and it has numerous applications in speech, language, and video processing. So some of the classical results are as follows. If we are given both if we observe both the latent variables and the ambient variables, then estimating the probabilities becomes very easy. If, on the other hand, we're only given the model parameters and the observations, then we can infer the maximum likelihood estimate of the latent variables by the Viterbi's algorithm, or get the entire posterior probability using the forward-backward algorithm. Both of these algorithms have complexity order k squared times t, where t is the number of samples we're given. Now, the interesting case that we're studying in this case is when we are only given the observation t's. And in order to estimate the model parameters, the classical algorithm is the expectation maximization, which basically iterates between these two steps. But the thing is that, well, the inference step is very costly, making this algorithm very slow and not scalable in practice. So quite recently, people have come up with methods to construct sufficient statistics that does not grow with t in order to estimate the model parameters. The first attempt is to consider pairwise co-occurrence probabilities, which factors into this form, and basically it forms a non-negative matrix factorization, omega equals m theta m transpose. Also this ambient probability, yt and yt plus 1, can be easily estimated using just counting the pairwise occurrences and normalize. But the issue is that NMF lacks identifiability in general, which means we can have a factorization that agrees with the observation of pairwise co-occurrences but does not agree with the other information that is lost when constructing the second order statistics. In order to have identifiability guarantees, people have proposed using higher order methods. And basically, if we look at triple occurrences conditioned on the current latent variable, then the probability factors into a tensor canonical polyadic decomposition, which guarantees identifiability under mild conditions. But the thing is that if we go to higher order, then first of all, the complexity still goes pretty high, especially when n, the number of the state space of the observations, is large. And also, if we rely on third order estimates, then we still need quite large number of samples to get reliable estimates, and in the paper we show that it is always less accurate than the second order estimate. So what we propose is to still go back to the pairwise co-occurrences method, and our proposed formulation is on top of the non-negative matrix factorization model, we try to find the one that has the minimum determinant of theta. And we show that if a assumption called sufficient scattered is satisfied for the emission probability, then we can uniquely recover the model parameters on up to permutation. And the sufficient scatter condition is a very interesting condition that we discovered a few years ago. And it is a geometric assumption, and basically it works for non-negative matrices. And a tall non-negative matrix, if the rows of this matrix is well spread out in the non-negative ortho such that the conic hull contains this special elliptical cone as a subset, then this matrix is sufficiently scattered. Some of you may be familiar with the so-called separability assumption, which says that the rows of M should contain the coordinate vectors. And we can easily see that this is a special case of sufficient scattered, because if the points are at the edges, then of course the conic hull is a superset of this circle. Furthermore, we show that if a matrix is sufficiently scattered, then it's sparse and almost equivalent to sparsity. So latent sparsity usually leads to identifiability guarantees using the special formulation that we propose. On synthetic data, we show that this indeed works much better in terms of recovering the model parameters. Here we keep 20 latent states and 100 observed states, randomly generate the transition and emission probability, and we let the number of samples goes from 10 to the 6th to 10 to the 8th. And comparing with some of the tensor-based method and non-negative matrix factorization, we see that the recovery result is much better, even going down to 0, whereas the others still have a large gap to fill. Finally, we apply this to the application of topic modeling. The most well-known topic modeling methods is the so-called bag of words, which ignores the ordering of the words. But here we take that back into consideration and assume that each document is generated from a hidden Markov model, where the latent space are topics and the observations are words. So, and the topics evolve as a Markov chain, which is, in our opinion, a very reasonable assumption. It actually includes bag of words as a special case because a Markov chain contains IID samples as a special case. Now, one of the main advantage of using a Markov chain, hidden Markov model to model a document is that, well, each word is associated with the topic, and we would expect that the topic evolution does not change rapidly in a document. And that is indeed the case if we use hidden topic Markov models to infer the topics of each word, whereas using a bag of words model, then the inferred topics changes rapidly. And finally, if we use word co-occurrences to estimate the topic matrix and evaluates its quality, we see that in terms of coherence, hidden topic Markov model is much better than some of the classical bag of words methods. Thank you for your attention.